Okay, welcome to our day 2 review of quadratic functions. So what we learned in our last lesson was that a quadratic function is one in which the term with the biggest exponent is x squared. So the graph, if you have a term that's x squared and that's the highest exponent, that's the highest order term, the graph ends up being a curve with a distinct maximum or minimum, and it's called a parabola. We learned that the slope of the graph increases or decreases by the same amount every time, and so the slope is a linear function. And then we also learned about vertex form, in which the quadratic function looks like this. And if the quadratic function looks like that, the vertex will be at the point h comma k, and a is kind of a scale factor that tells you how wide or skinny or what direction the parabola opens. In today's lesson, we're going to learn that a quadratic function can sometimes take other forms than vertex form. So we're going to explore a new form today called factored form. And we'll do that by looking at, there's a Google Doc in the description. And if you want to click on the Google Doc and open it, you can follow along. Today's lesson is a little shorter, but we'll do this exploration with a word problem. So in this situation, humans have finally colonized Mars. I took this from, by the way, Connected Math Project. The volume called Frogs, Fleas, and Painted Cubes. It's just adapted slightly, but I wanted to give credit where credit's due. So in the year 2100, let's say you're part of a group establishing a colony there, and you can stake a claim for a plot of Martian soil, anything you can enclose with 40 meters of laser fencing. So the first prompt is to sketch a few rectangles that have perimeters of 40 meters. So I encourage you to pause the video here and just draw a few rectangles and check the perimeters to make sure they're 40 meters. Okay, and now you can resume. And so I'll do a few with you. So maybe you started off by drawing like your first basic rectangle with a perimeter of 40 meters. And that was the one in which it's a square and every side has a length of 10, right? Another shape you might have drawn would be maybe that one right there. And in this one, let's see, each of these longer sides is 15. And then each of the shorter sides is, sorry, I can't draw today, is 5. So 15 plus 5 plus 15 plus 5 is 40. So that one would work. And then maybe you got a little more creative, and maybe you even did something like this. And then in this case, maybe like the long side is 19 and the short side is 1. So you may have noticed as you were drawing your rectangles, there's a pattern where the length and the width added together had to be 20, because a length and a width is half the perimeter. So it sort of gives you a clue of how to approach the problem. We're going to make a graph of these values. And let me go ahead and turn off the draw and zoom. So we'll get rid of those rectangles. We'll make a table of all the rectangles with a perimeter of 40 meters. Now we're not going to list all of them, but we'll try to be systematic about it. And let's start with where the width is, say, 2, and we'll just go up by 2's every time. 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay, and if we want to be fancy, we could add the 0 on this end and the 20 on this end, but they end up being pretty trivial rectangles. So if the width is 2, the length has to be 18. And then the area in this case, 2 times 18 is 36. So we put that there. And then on the next line down, if the width is 4, the length plus the width has to add up to 20. So the length would be 16, and 4 times 16 is, oh gosh, let me think about this one. 32 is 2 times 16. 2 of those would be 64. There we go. I'll pause while you finish filling out the table, and then we can compare our answers. Okay, so I've got the table filled out now. I made all the combinations of width, length, and area, and definitely noticed some interesting patterns. For example, the width increased by 2 every time, and the length table was identical to the width. It just was in the reverse order. And then when I started multiplying width times length to get area, I saw the area increase up to a point, and then it started decreasing again as we went back down the table. But the maximum area was the 10 by 10 rectangle. So if you're looking for maximum area in your plot, you definitely want to do the 10 by 10. So next we're going to graph it, but we're going to graph this showing length on the x-axis and area on the y-axis. So I've already scaled my y-axis and it's going up by tens. So 10, 20, 30, 40, 50s right here. 60, 70, 80, 90, 100's right there. And then for my x-axis, which is length, I'll put an L there. I'll make that go up by twos so I can just graph each point one by one. So I'm going to change this to be a freehand so that I can get good size dots, and then we'll go ahead and start graphing. So 18 for the length, 36 for the area, means you go 2, 4, 6, 8, 10, 12, 14, 16, 18. And then to do 36, we go up by tens, 10, 20, 30, 36 would be partway between the 30 and the 40. So there, that's 18, 36. And then we'll go to the next one, 16, 64. 16's here, and then we'd go 10, 20, 30, 40, 50, 64, okay. 14, 84. 14 would be just one to the left of the 16. To do 84, we go 10, 20, 30, 40, 50, 60, 70, 80, 4. Next we do 12 and 96, and then we do 10 and 100. 100 is exactly on this line, and then we'll go back down to, interesting, 8 and 96. That'll be there, and then we go to 6 and 84. That'll be there. 4 and 64. That'll be there, and then 2 and 36. And you probably recognize the shape that you just made. So this relationship between the length and the area makes a parabola, and so that suggests that the relationship we're looking at is a quadratic. So I'll give you a second to catch up with that graphing, and then I'm going to turn off the drawing tools. So the graph of this relationship looks like a parabola, so it must be a quadratic equation. Interesting. Now when we write the equation for factored form, we're going to write the equation where area is the dependent variable because I graphed it on the y-axis, and length is the independent variable. So you know, of course, I'm going to get to the factored form of the equation in 3 steps. You know, of course, that length times width is equal to area, right? Sorry, let me make that be a capital A. And then we also know the length and the width have a relationship to each other. So the length and the width have to add up to 20. So we know that the width is equal to 20 minus the length, right? Because they have to add up to 20. So that means that if you write length times width, but write it all in terms of length, we can just take the 20 minus L and substitute it where the W is right there. So your area is equal to length times 20 minus the length. Oh, let me finish that as a parentheses, or I usually don't write it with an X in front of it. I just write the symbol and then the parentheses smushed together. So A is equal to length and then parentheses 20 minus length. So this form of the equation is called factored form. It doesn't look like a quadratic. And it doesn't look like a quadratic because there's no L squared term in it. At least it's not obvious, right? But as you'll see when we expand it, there is an L squared term. It's just kind of hiding because it's written in this factored format. So you may remember from when you were, a young child earlier in middle school math or Algebra I, that if you have like an A outside of the parentheses and then B plus C in the parentheses, you can write that as AB plus AC. So this is the distributive property. A times quantity B plus C is the same thing as A times B plus A times C. So we're going to apply that same property to our equation for area. And we'll do that by saying A equals L times 20 minus L. So A equals, we do L times 20, which is 20L. minus L times L, which is L squared. And then that's kind of interesting because there's that L squared term that is the hallmark of a quadratic. And if we write it in descending order by exponent, negative L squared plus 20L. So I just switched the location of the L squared and the 20L. When you write quadratic functions, it's really common to write them in descending order by exponent. So this is the same function, and this is called expanded form. So factored form and expanded form. Not all quadratic equations can be easily written in factored form, but we're going to explore a few of the simpler examples for how you can go between factored and expanded. For the remaining part of this worksheet, there are some example problems, and they're written in factored form, and then your job is to convert them to expanded form. So this might be something that doesn't look like a quadratic, but when you expand it, you'll see that it actually is. So in this case, for example, x times x is x squared. Whoop, I can do this. X squared plus, and then 2 times x is 2x. Notice that x times x is not 2x. X plus x is 2x. X times x is x squared. It's a different notation. If you add it to itself, there's two of them. If you multiply it by itself, it's squared. Okay, in this example, okay, maybe try it yourself before I help you out with it. Pause. Okay, and so the way that we expand this one is you'd multiply x times 3x, and that would be 3x squared. Hitting the wrong key every time, kids, sorry. 3x squared plus x times 100 is 100x. So this is also a quadratic. Next one over. Again, pause, try it yourself. Check your work with me. 6x squared minus 10 times 2x is 20x. So remember that that sign in front of this number here travels with it. This is basically the same thing as doing plus negative 10. So this is effectively a negative 10 times 2x. Okay, next one. This is going to be a multi-step problem because there's an extra term here, so we're going to have to simplify when we're done. X times 9x will be 9x squared. Okay. X times minus 1 would be negative 1x. You don't need to write the 1. If there's only one x, you can just say minus x. And then you would keep the plus 7. And then I would inspect the equation to see if there's any simplifying that I can do. You can combine terms if they have the same exponent, the same variable raised to the same power. There's no terms that are x squared other than this one, no other terms that are x to the first other than this one, and no other single constants other than this one, so we're done. Okay, next one down. 14 plus x doesn't need to be simplified right now, so we'll keep that as it is. Plus x times x, as you know, is x squared. And then plus 10 times x is 10x. And then this one may be able to be simplified. Inspect your expression and see if you have any terms that have the same variable raised to the same power. We have two of them here, 10x and x. So they can be added together. And then that will end up being, I'll write them in descending order by exponent, x squared plus 11x plus, oh my goodness, what have I done? There we go, plus 14. X squared plus 11x plus 14 is that one in its most simplified form. Check out the description in the video for some Khan Academy problems you can do to reinforce this concept, and we will see you for tomorrow's lesson.